The storm didn't arrive like a warning. It arrived like a correction. For years, everything had looked stable. The houses stood. The routines held. Nothing seemed wrong enough to question. And that's how most failures begin. Not with chaos, but with confidence. When people think about buildings collapsing, they imagine force, violence, a sudden, overwhelming impact. But that isn't how nature usually works. Nature doesn't rush. It tests, slowly, patiently, looking for assumptions that were never meant to survive pressure. When the wind finally came, it didn't attack everything equally. Some structures vanished. Others didn't move. Not because they were newer, not because they were stronger, but because they behaved differently under stress. That difference began long before the storm. At the moment someone decided what shape a house should be. Square buildings feel inevitable to us. They always have. Straight walls are easy to measure. Corners are easy to join. Right angles give the impression of order, precision, intelligence. We associate them with planning, with civilization, with control. So when something breaks that pattern, when a structure curves instead of corners, it doesn't just look unusual. It feels wrong. People don't laugh because it's fragile. They laugh because it challenges what they've stopped thinking about. And that's the first mistake, because wind doesn't recognize familiarity. It doesn't care what feels correct to the human eye. Wind responds only to physics. It reacts to surfaces that interrupt its flow, edges that force it to change direction, corners that trap energy and turn motion into pressure. This is where the story quietly changes. A storm isn't a brute force event. It's a selective one. It doesn't destroy everything. It exposes what was already vulnerable. Corners, the very features we rely on for convenience, become points of leverage. Flat walls become barriers where pressure accumulates. Design choices made for ease of construction turn into weaknesses under stress. And the wind finds them. That's why asking, "Why did one house survive?" misses the point. Survival isn't the mystery. The real mystery is this: why do so many designs quietly assume that extreme conditions will never arrive? Why do we confuse what is easy to build with what is safe to endure? Because once that assumption is challenged, this stops being a story about a single storm. It becomes a question-iddle about how we design things at all. And it leads to a deeper, more unsettling question, one that doesn't have an answer yet. When we talk about wind-destroying buildings, we often describe it as violence, as if air hits a structure with brute force and simply overwhelms it. That description feels intuitive, and it's misleading. Wind does not destroy by impact alone. It destroys by how force is guided, delayed, and concentrated by shape. In physical terms, wind is a moving system. It flows continuously, adjusting to every surface it encounters. What matters is not how fast the air moves, but what happens when its movement is interrupted. A flat wall forces air to slow down abruptly. When movement slows, pressure rises. This pressure has to go somewhere. At a corner, the problem becomes worse. Air reaching a corner is forced to change direction suddenly. Part of the flow splits, part of it spins. This spinning motion, turbulence, traps energy instead of releasing it. Turbulence is not random chaos. It is a mechanism that amplifies stress. Energy that would normally pass by is forced to linger, pushing repeatedly against the same point. This is why engineers use the term stress concentration. It describes locations where force accumulates far beyond the average load. Corners create these locations naturally. A square structure doesn't fail everywhere at once. It fails at specific points, where geometry gives force time and leverage. This is why storms often peel roofs first, rip walls from corners, and tear buildings apart piece by piece instead of crushing them outright. A curved surface changes the interaction entirely. When air meets a curve, it is not forced to stop. It is redirected gradually. The flow remains smooth. Pressure spreads instead of building. No single point carries the full load. This is not about strength. It is about distribution. A round structure does not resist the wind. It avoids creating places where resistance becomes destructive. Flat walls challenge moving air. Corners provoke it. Curves do neither. They allow the wind to remain what it wants to be, a flow, not a battering ram. This explains something that often goes unnoticed. Buildings rarely fail because the wind is strongest at one moment. They fail because stress is allowed to build, cycle after cycle, until materials fatigue and connections give way. Once you understand that, survival stops looking accidental. It becomes predictable. And it leads to a deeper realization. If shape determines how force accumulates, then the same principle must apply to something else storms exploit just as effectively. Not force, but loss. Specifically the loss of heat. And that is where the next failure usually begins. When people ask why some buildings stay warm longer than others, the answer they have thicker walls. Better material per layer. That answer isn't wrong. It's incomplete. Heat doesn't vanish, it moves, and it leaves a building through the paths that design quietly creates for it. Every enclosed space loses heat. What matters is not whether heat escapes, but where it escapes first and how quickly that loss accelerates. In square rooms, air movement is uneven by default. Warm air rises, cooler air sinks, but it doesn't circulate smoothly. Corners interrupt flow. Where walls meet, air slows down. Movement weakens. These areas become zones where temperature stabilizes lower than the rest of the room. Cold doesn't spread evenly. It settles. Once colder air settles in a corner, it stays longer. The surrounding surfaces cool faster. Moisture begins to condense. This is why corners are almost always the first places where cold is felt, where dampness appears, where mold begins. These effects are subtle at first, but heat loss is not linear. Small temperature differences create gradients. Gradients drive faster energy transfer. Loss accelerates where imbalance exists. A circular space changes this behavior. Without corners, air has fewer places to stall. Movement remains continuous instead of fragmenting. Temperature differences flatten rather than concentrate. The space doesn't become warmer by magic. It becomes thermally stable. Heat still escapes, but it does so evenly, without creating localized cold zones that pull energy out faster. This same principle applies to the outer shape of the building. For a given interior volume, a round structure exposes less surface area to the environment. Less surface area means fewer opportunities for heat exchange. This is not tradition. It is geometry. That is why objects designed to retain heat or pressure, vessels, tanks, containment structures, avoid sharp angles whenever possible. Corners are efficient at concentrating more than stress. They concentrate thermal loss. Ancient builders didn't explain this in scientific terms. They learned it through consequence. Structures that stayed warm were reused. Those that bled heat demanded more fuel, more labor, and more risk. Over generations, form followed experience. Modern construction often reverses this logic. Instead of reducing loss, it compensates. More heating, more systems, more energy. That solution works as long as resources are abundant. But when conditions become extreme, design decisions made for convenience resurface as vulnerabilities. Once you understand how shape governs heat behavior, another question becomes unavoidable. If geometry controls how warmth leaves a space, Why do we still design buildings that make loss inevitable? The answer is not thermal. It is human. And that is where the next part begins. At this point, the technical reasons are no longer unclear. Curved forms handle wind more gently. They distribute stress more evenly. They reduce thermal imbalance. So the question changes. If these advantages were observable, why did square buildings become dominant? The answer is not ignorance. It is priority. Square structures are easier to produce. Straight elements are simpler to cut and transport. Right angles simplify measurement. Flat walls make expansion predictable. A square building can be planned quickly, built by less specialized labor, and replicated with minimal variation. In short, it is optimized for efficiency in construction. Round structures are not. They require curved components or complex joints. They demand precision. They resist modification once built. From the perspective of growth and speed, these are disadvantages. So the choice was made quietly, not because square buildings performed better under stress, but because they performed better under normal conditions. And normal conditions dominate decision-making. Most structures are not designed for rare events. They are designed for daily use, average weather, and predictable loads. Extreme conditions are treated as exceptions. Exceptions are postponed. Postponement becomes habit. Over time, habit turns into tradition. Once a design becomes standard, it stops being questioned. Its weaknesses are accepted as trade-offs rather than flaws. This is how suboptimal systems persist. They function well enough most of the time, and most of the time feels sufficient. But extreme events are not about frequency. They are about consequence. Wind does not need to arrive often to matter. Cold does not need to persist every winter to be dangerous. They only need to arrive once. Square buildings fail in familiar ways. Corners concentrate force. Flat surfaces collect pressure. Thermal loss accelerates where geometry creates imbalance. None of this is surprising from an engineering standpoint. What is surprising is how consistently these factors are ignored. Modern construction often compensates instead of correcting. We reinforce joints instead of removing stress concentrations. We add insulation instead of reducing loss pathways. We install systems to manage problems created by shape. As long as energy is available, this works. When energy becomes limited, or conditions exceed expectations, the original design choices resurface. The dominance of square buildings is not a technical failure. It is a human one. It reflects what we chose to optimize for: speed over endurance, convenience over resilience, familiarity over adaptation. Once this is understood, the story no longer belongs to the past. It becomes a mirror. And it sets up the final question. Not about buildings, but about how we design systems when failure actually matters. By now, the mechanics are clear. Curved structures distribute force instead of concentrating it. They guide wind instead of stopping it. They reduce thermal imbalance instead of amplifying it. Nothing here is symbolic. Nothing relies on tradition or belief. These outcomes follow directly from geometry. The round structure did not survive because it was exceptional. It survived because it removed predictable points of failure. It offered no corners for force to gather, no flat surfaces where pressure could accumulate, no hidden zones where heat could leak faster than the rest. It didn't resist the environment. It denied the environment leverage. That distinction matters. Most failures are not caused by overwhelming force. They are caused by design decisions that allow stress to build quietly until materials fatigue and systems give way. This is not limited to architecture. Any system designed primarily for convenience under normal conditions will expose its weaknesses under extreme ones. Buildings fail this way. Infrastructure fails this way. Organizations fail this way. Failure always appears at the edges, where assumptions stop holding. Ancient builders did not possess better knowledge. They faced harsher constraints. Without abundant energy, without mechanical correction, design had to solve problems permanently. Shape mattered because it could not be patched later. Modern design often follows the opposite logic. Instead of eliminating weak points, it reinforces them. Instead of reshaping flow, it adds systems to counteract it. This approach works while resources remain available and conditions stay within expectations. When either changes, geometry takes control again. Stress concentrates where it always has. Heat escapes where it always has. Failure follows the same paths it always has. What we often call progress is simply the ability to delay consequences. The deeper lesson of the round structure is not about returning to older forms. It is about recognizing how much of modern design is built around assumptions rather than behavior. Nature does not respond to intent. It responds to interaction. Wind reacts to shape. Heat reacts to gradients. Force reacts to concentration. Design that ignores these reactions creates problems that must be solved later with energy and maintenance. Design that accounts for them removes problems before they appear. That is the difference between resilience and correction. So the real question this story leaves behind is not architectural. It is fundamental. When faced with forces we cannot control, are we designing systems that cooperate with them, or systems that merely endure until conditions exceed our assumptions? Because survival is rarely decided in the moment of crisis. It is decided quietly. At the moment, design choices are made and never questioned again.